我们在上课。
探讨对正确钢铁。正在研究探讨对正确钢铁，正在研究。先探讨。你提出探讨。
So let's recall what we learned last time. The main result we obtained last time was the so-called final rule. And we employed this standardizing approach. There are two key ingredients in this approach. First, we assume the commutation relations. And we also promote the equation motion to the operator equation. We try to insert equation motion into the correlators, and we go step by step. And we also, this is the perturbative approach, so we also assume a small parameter expansion perturbative. We assume the coupling is small. More coupling. So finally, we realized that in order to solve these correlators in the interacting series, we can actually do the order by order expansion. Okay? Order by order expansion. This is a systematic approach to solve this interacting series. So let's briefly summarize the obtained with this final rule. So basically, during the outcome, we first derive the result and then graph the result. Okay. And the point is, once you get this graph, once you get these rules, I can skip this derivation. Okay. If you hand me a problem, I can immediately draw the graph, and then I assign the rules to the graphs. I can write down the result. Don't need to do the calculation again. Fine. So what is the rules? The rules basically says that whenever you have a graph, something like this, for example, x1, x1 is the external point, x is some internal point. Whenever you have such an interval, you assign a propagator, something called d1x. And whenever you have something like y, x2, then you could assign the propagator like d2. Okay? And this is the rule. This is the number. This is the piece of the rules. And then, if you have something like a vertex, something like this, and this position of this vertex, for example, is x, then you should assign a coupling constant times the imaginary I. Okay, times the imaginary I for each such kind of vertex. And eventually, you have to sum over all the diagrams. All the lines affected. And the vertex is over all the lines compact. Position of the vertex integrated. Okay, it's almost done. Okay? Be careful, there is a so-called all diagrams, means all the possible diagrams you have to take it into account, okay? For a given problem, Sometimes it's confusing here. How do I really, I sum over all the diagrams. The key point is to distinguish the given data and the possible appeared data. There's a difference. Okay? For the given data, it's quite often it's already set in the problem given. Okay. For example, someone asks you to compute this 4-point function, then they will tell you which point the insertion. Okay. Meaning this external point. These are given data. For example, x1. Okay. Of course, the pattern of this vertex is also given because interaction theory tells you which kind of vertex possibly appear. Okay. For example, bicubic theory. This is the 3 vertex. Okay. If you have a biquartic, you have 4 vertex. Okay. And then, apart from that, all other possible appeared diagrams you have to really take into account. All of them. Okay. But you shouldn't be scared because, as we saw last time, usually these are finite diagrams. Usually it's a finite number of diagrams. Okay. Not that much. And the last, we also have to be careful when all the above stuff picked over. Finally, we have to divide it by a symmetry factor. Right. Okay. The symmetry factor appears, or you have to divide essentially because there is an overcounting. There is an overcounting. Okay. Okay. So do you have any question about what we learned about the Feynman rules last time? So today we're going to continue to develop these Feynman rules. As you can see, last time we talked about what this rule is about the position space correlation function. Okay? Position space, all these x, y under the position of this list time. So as we are motivated in the very beginning, we want to calculate the S matrix. And we define the S matrix is actually in the momentum. Okay, then naturally we have to also develop the Feynman rules in the momentum space. So this is the next step. Momentum space. How do we get there? Then naively you might say, okay, the only thing I have to do is just do Fourier transformation, right? Because that's what we learned before. Whenever somebody tells you to go to momentum space from condition space, then you do Fourier transformation. Right? Indeed, this is true. But to be more precisely, here we have to employ this formula we learned last time, so-called LSD formula. Using LSD formula, there's a precise way you can go from the position space time ordered correlation function, okay, to this S matrix. Here by momentum space, Feynman rule, essentially, what do we mean by this? Is essentially the calculation rules to compute this S matrix. Okay. S matrix, because we defined the last time S matrix, we defined it by this initial momentum eigenstate, right? Input and output, right? Ingoing state, and outcoming state, and then there's a non-trivial interaction in the intermediate. Okay, you have to calculate this. So we developed this momentum space Feynman rule and essentially want to compute that one. So then let's use this LSD formula. We also learned that the LSD formula is basically the Fourier transformation. Okay, it's basically the Fourier transformation. So you might saw already last time this formula is a bit long formula, right? You may be scared by this formula, but it's actually a very concrete formula. So I think the best way to understand this or perform the calculation is start from one example. So let's start from this example. We have a few graphs last time, right? There are graphs, and one particular graph it looks like this. So let's start from one particular. Okay, well, 5-qubit series. Here's one particular graph, right? So what is this? Can you employ these Feynman rules to write down this position space correlation function for this graph? It should be easy, right? Last time we derived it using Schrödinger dice, but now forget about this Schrödinger dice. The tedious process in intermediate process, forget it. Okay, just using these Feynman rules, you can write down the result. So what is that? Let's just do step by step. So first, let's count. There are 2, 3 versions. Right? One here, one here. See? For each one, you have to find a constant and I, right? And there's a IG squared. Then there's a minus G squared, right? Minus G squared to appear. Now, there's 2 propagators look like this. There are 2 vertex look like this. So, and we have to integrate it over this x, and then also okay. So eventually, there should be a d1x, d1x, and there are dxy, but there are twice, right? So dxy squared, and there is a dy2, and this x and y has to be integrated over. dy. Okay, that's it. Now last step, we will divide by the symmetry factor. What is the symmetry factor? In this case, is 2, right? 2, because if you switch these 2 lines, the graph is the same. Okay. So then this will be very primary. Okay. For this graph. Now let's use this particular graph result, perform this LSZ calculation. Then you go to the S matrix. Okay. Even though this looks a little bit trivial, it's not completely trivial. It's a little bit trivial in the sense that you see. Yeah, we will see that in terms of S matrix. After LSZ, you see this diagram. Then when everything goes to the momentum space, this looks like one particle incoming and one particle outgoing. Okay, it's a little bit trivial. There is a non-trivial process can happen in medium. It's not 2 to 2, it's 1 to 1. Okay, right? Last time when we define the S matrix, we usually go to 2 to n or 2 to 2. You have 2 particle incoming particles. They scattering and then become the others. Okay. In this case, you might get some 1 to 1. Okay? 1 to 1. So let's do this calculation carefully. So remember that the dxy we also derived before some time ago. This is the p integral for this momentum space Feynman property. This is dxy. Okay? Remember that? We employ the I plus I epsilon description, right? We always assume epsilon is positive, small constant, which should be set to 0 eventually. Okay? After you perform all these calculations, integral calculations, it's set to 0. Well, you just plug it in, right? There's a d squared in the d. This is what is d defined in this way. You just plug in, do the calculation, right? Just do the calculation. So let me do it for you. Then do this calculation. Okay. You have 2 integrals y. Okay, it's 2 integrals y. Now you have 4d basically. Okay. Each d will carry a p integral, you see? Right? Each d will carry a p integral. Then to distinguish those different p integrals, label it as p1, p2, p3, p4. Okay? So they are just independent. So let's use this different p P1, P2, P3, P4. And in particular, I use P1 and P2. I use P1 and P2 to label this momentum for this dy(x) and dy2. Okay. And I use P3, P4 to label this. Okay. To label this to dxy. So just plug in, and then the remaining thing will be the. Yeah, because P1 is for the d1x, so P1 coupled with x1 minus x here, and P2 coupled with y minus x2, and P3 coupled with x minus y, and there's also P4 coupled with x minus y. Okay. And then, of course, you will have 4 Feynman provocators or momentum space, right? So you should write down them. And that's it. Okay. You plug in, this is what you get, right? This is what you get. Now, how to calculate this one, right? You have to ask yourself how to calculate this one. It's a little long formula, but it's not difficult, right? Because many structures repeated, right? Okay, you can change this, flip this integration order to simplify things. That's the immediate thing you should realize, right? Now you can do these 2 integral first, right? So what do you get? When you do this x and y integral, what do you get? Does anybody know? What do you get? That's right. You get their function, right? Yeah. Okay. You get their function, right? Because this x integral, the only part associated with this x is this exponential IPx structure, right? You see, there is the exponential IP1x. There is a IP3x. You see, here, there is an IP4x, right? Right? That's it. The only other is not. It's nothing to do with x, right? Or other variables, nothing to do with the x. Or other integrand, it's nothing to do with the x. That's the only thing you have to integrate. So when you do the integral for the exponential IPx, of course you will get that function. Okay, that's the definition. So you do this one first. Will give you a third function. The third function is minus P1 plus P3 and P4. Okay, this is their function. Now, similarly, you do this y integral, right? You do this one. This will give you another third function. Okay? You get 2 third functions, right? You get 2 third functions. Then, once you have third functions, then immediately you realize that if you integrate over further, some variable appears in this third function, okay? Then you kill the third function, okay? But you set the constraint to maintain this entire thing in the third function is 0, right? That's what third function is defined, okay? Third function is defined through integral, okay? Now what do you do? You have 2 delta. What do you do? It's up to you, right? You can choose which variable, which momentum variable line you can do it. Okay, for example, I can choose to do the P3 first. But you can also go before. Then next step, I integrate over P3. Okay? I integrate over P3. I do the P3 integral. Then what do you get? Then you can choose this third function. Okay? See, if you like to clear this third function, right? Then you set everywhere else P3 equals to P1 minus P4, right? That's it. Then you throw away the integral. Then this gives you P3 equals to P1 minus P4. Okay? Is that clear? Now, then this third function, you have another third function, right? I haven't touched this part, okay? But the point is, because third function already set P3 equals to P1 minus P4, then this third function simplifies. You see? Simplified to what? It simplified to P1 minus P2, okay? You just plug in that P3 value. Okay? So we're almost done, okay? You see? Almost done to simplify the integral or to calculate this integral. So last step, because I already integrated over P3. I want to change P4 to K, for example. So we label it. It's not a big deal. Then after all these steps, you get result. Don't forget you have four propagators in momentum space. Okay, 4 propagators. But for the propagators, you have to also, set correctly what we just did. We integrate, we clear the third function, then there are constraints left over. Okay, that's it. Okay, we did it shorter, right? Compare with that formula, and we will finish the 3 integrals. There's still 3 remaining. Okay, but this is good enough to do the LSD transformation. Okay, to use this LSD formula. So what is the LSD formula? So in this case, the LSD formula, I'll write it for you. Remember. We call LSD in this case, okay? Okay, remember that. The LSD depends on what are the incoming and outgoing particles. LSD is for the purpose to calculate the F matrix, right? F matrix. So in this case, there's only one particle incoming and one particle going. So in this case, we need one incoming momentum and one outgoing momentum. So remember that in this LSD, for the incoming momentum, we have to assign a minus sign, I, Pi. I is the incoming, okay? That's one example, and Pi squared. Okay? There are a few factors, right? Remember that? That's LSD, right? LSD. And if you have one outgoing, then you should assign a plus I. T F. F means the final, in means the initial, final, okay? Incoming and outgoing. X2, and there is a P F square here, okay? And this is the two factors in front of this Z formula, okay? And then the remaining thing is what? Is the time ordered correlators, right? Time ordered correlators. This is the Z for the interacting theory. Okay? Interacting. This is the SD. SD tells you go from the time ordered position space correlation function to the element. Right? So I'm going to write more explicitly the LSD for this particular graph. Okay? For this particular graph. Okay? Because this is a 2-point. This is a 2-point time order, right? Correlation function. This is the one piece contribution to the one graph contribution to the 2-point time order position space correlation function. LSD tells you how you can go from here to the S matrix, okay? Using this kind of transformation, okay? This is, as said, this is almost a Fourier transformation, as you can see, right? It just transforms this from position space to the momentum space, okay? But with two additional factors, E squared, okay? E squared. You can also write this. You can also write this into some box. That's the same thing, right? You plug a box into the momentum space. This is P squared. Okay, P squared. So this is the LSD. Now, I already have the result for this part. You see, for this part. Even though this is only one piece, I didn't sum over all the possible. So let's do piece by piece. I already have a result for this one, then the only thing I have to do is do this integral. See? Do this integral. So let's do it. So use LSD. Sorry, I think I dropped some factors. There's some factors. The 2-part force. Check carefully. There's also a third time. Constant U1 minus P2. See? Because it comes from here, right? Okay. Now let's do the LSD. So how to do this? You basically plug in T1 result, okay? Plug T1 result into LSD. Then you have x1, x2 integral. You see, this part is basically that formula, okay? That formula. And what do? You can do the x1, x2 integral first, okay? You see? So what you get? Just count. Again, like what we did before. If you do x1 integral, then there is a pi x1, and also there is the x1 here, right? See, there's x1 here, and everything else nothing to do with x1. You see? Okay, again, like before, when you can first do x1, x2 integral, you get their function. You see, right? You get their function, right? This x1 integral will give you their function. T1 minus pi. Okay. With that set their function p1 minus p5. And you do x2 integral. You also get their function p2 minus pf. Okay. You see, this is very natural because now you perform the integral over, you have all the p2 integral, right? Now you have their function associated with p1 and p2. It's good. You just perform the integral over p1 and p2. You just set everywhere p1 equals to pi, everywhere p2 equals to pf. You see, this is very natural. Now you don't have a p1, p2 variable anymore. Because pi and pf are given data, okay? These are the given data. Given data. In LSD, these are the given data. It tells you a particular count with S magnitude for which particular initial momentum, okay? And the final momentum. So that's good. Then you do this P1 integral and P2 integral afterwards. Then you get eventually, but there is a small subtlety here, okay? There's a small subtlety here. Now you ask, okay, after I perform this P1, P2 integral, follow that afterwards, then I will set this P1 equals to Pi, right? That's good, right? And if you are very, very careful person, you might still vary this. There's I epsilon, you see? You see? This is I epsilon, but this is only a Pi square. What do you do with I epsilon? Can anybody say something? Let me tell you, let me check whether you really understand this I epsilon prescription. So how do you do with this I epsilon in this case? What do you do with I epsilon? Yeah, I epsilon did nothing. You can throw it away. Why? Anybody tell me why? Because I epsilon only matters when you have a social integral. If the integral does not exist, you can always set it to 0. Okay? You see? In this case, it happens, right? Because P1 integral appears by their function. That's their function. Okay? Okay? You can just do this P1 integral. It's amount to set everywhere P1 equals to Pi. Then this propagator becomes this is I over Pi squared plus I epsilon. Okay? But you ask, what does it mean? What do we mean if I have a Pi squared plus I epsilon? I epsilon in this case means nothing. There's no integral associated with Pi. Pi is a given momentum. It's a given momentum. Okay? Pi is a particular momentum. It's known. It's a value. It's a number. Okay? It's a given momentum. So I epsilon in this case does nothing. Okay? I epsilon only matters when there's an integral associated with this momentum, as we learned in this second lecture or third lecture, right? Only in that case you have to deal with a contour integral, okay? In order to perform that integral in the four momentum space. So you have to really solve this contour integral. Only in that case I epsilon matters. If you don't have such kind of issue or problem, contour problem, then you throw it away. In case it happens. So you throw it away because that's essentially what we define this epsilon prescription, right? So always emphasize it after the integration. Finally, we set epsilon goes to 0. Remember that? Here you can set it to 0. Okay. Then it really cancels. Then this cancels with this one. You see? This cancels with this one. Okay. There's some constraint. After this, cancels with this one. Okay, okay, very good. From here, you can see why we add such fancy factors. This one in front of LSD. You see? You see? We didn't explain clearly, but here you should be very, very precise to understand why. You see? Because this box square or p square factor in front of LSD formula was designed to cancel this external propagator. Okay? You see? Because this pi square, pf square is the external propagator. By external propagator, I mean this external lines. Okay? See? This external lines. Okay? This external lines. After Fourier transformation, this external lines in principle also contribute to 1 over p square propagator for each one. But LSD formula designed, there is additional factor p square, a few p square factors there. That's what LSD formula was designed to cancel those. You see, so there's a multiply. Actually, this is precisely true in general, because whenever you have how many incoming particles and outgoing particles, this is always true, right? If we learn LSD, LSD was prepared for each incoming particles, there are such factors. And for each outgoing particle, there are also such factors. So they are precisely cancelled, okay? Precisely cancelled. So that's why, additional to the Fourier transformation, there are some additional factors here, okay? Additional factors. So mathematically, we almost done, because after all these calculations, you eventually arrive at the S metric. Only left over integral is k. Is this k? Okay. Then the integrand becomes pi minus k plus I epsilon. Here epsilon you shouldn't throw it away. Okay. Okay. So this is the typical calculation in this quantum field theory. When you go step by step, you should keep in mind what you're doing. Okay. You cannot just blindly go, then you just somehow confused. Okay? For each step, you have to be very clear what you're doing. Okay? This we cannot throw it away because there's a k integral. It matters. Okay? So this is the final result. This is the final result. This is the final result for this S metric for this particular graph. There's only one k integral. One k integral. So go back to search what is k. K is P4, right? P4. K is come from P4. P4 comes from some momentum associated with somewhere here. Okay? Yeah, it's not the external momentum. Some momentum in the internal line. Okay, so that integral is still there. And if you can observe something, it's actually a very nice result, because this is k, another is pi minus k. Okay, then it's natural to assign these two momentum in these two internal lines, you see? Because momentum has to be conserved, right? The total incoming momentum is pi. One internal line momentum is k. The other line must be pi minus k, okay? Right? So in this sense, that graph is more, can be explained more intuitively in the momentum space, right? You can do both. What I'm saying is, in momentum space is more intuitive. It's really describe an incoming particle and split into two, and then okay, becomes the final single particle. That's it. So there are some factors here. These factors should remind you when we define the S matrix, we also we also defined something called amplitude. Remember that? Right? The difference is, let me remind you, when we define the S matrix, we also define something called amplitude. Oh, we denote it as IM. Okay? Remember that? We define the IM in this way. Now this factor is nothing but this factor. This factor. Okay? And this graph only represents the piece separated from the identity, right? Because this graph is really characterizes the interacting piece. Of course, it belongs to the second term. Identified is the free part. Okay. Okay. So from this result, we can also read off IM. Also read out IM. So in this case, IM is minus g squared over 2. Okay, so final result is very simple. Okay, if you're only concerned want to know this final amplitude IM, that's it. That's it. Okay. Then, like before, we can try to make some rules. Okay, this is the calculation, but you don't want to do every time. You don't want to do the LSD once, again and again. Okay. You just want to, if you let me know the graph, the process, the real process, I can immediately write down the final result. You can do that, you see? You can almost do it, you see? That beautiful result, you can almost assign to this graph, you see? Okay? So what are the momentum space? Now we come to this momentum space. Primary rules. Okay. Before that, do you have any question about this calculation? Yeah, I suggest you go through it by yourself. There are some 2 pi factors, some many delta functions. Yeah, it's very interesting calculation. It's very precise. So now we can extract or summarize the momentum space primary rules. Like before, we just assign the mathematical structure to each building block of the graph. Okay, of the graph. So each graph here, we calculated this kind of graph. We have to stick into this graph. Okay, but make a different physical interpretation in some sense, right? If you want to go to momentum space, for sure you have to assign different mathematical structure to the same graph. Okay. Graph is this, the same graph, but interpretation now is different. Okay. Here there is an interesting question. I suggest you to think it yourself. Think it carefully yourself. You might wondering, you do some Fourier transformation about some given graph. why the graph does not change, right? The graph is still the graph. Do you know why? It's a mysterious fact, right? The graph, the interpretation was changed, but the graph is still the graph. Right? In some sense, the topology was unchanged. Okay, you see, all the topology was still there. The line, how this there's one loop or two loops or something. The graph is still graph, right? You see? Think about it. Now, for the graph in the momentum space, for each internal line, we assign a momentum space propagator. Okay, in this way. See, this way. So for each internal line, you have to assign I over P squared. There, I throw away the M squared. It's not a big deal. I'll cover this M squared. So for massive case, use the propagator. And for each vortex, like before, you have to assign I times coupling function. Now, different from the position space of primary roots, for external lines, no propagator. Right? Because LSD killed the propagator, right? No propagator, right? LSD killed the propagator. But that's fine. No propagator. Instead, for each external lines, it assigns some given momentum data. See? Because physically, this line really represents some incoming particle, right? And in the S-metric sense, or in the momentum space, this incoming particle, we described it. We assign this particle to a particular momentum, right? So each external line assigned to a given momentum data. Like PI or PF, okay? Okay? But of course, you could have many. You have many. P1, P2, P3, P4, all the incoming and outgoing is many, also many. Now, as we learned in high school, because every line, seems every line are associated some momentum, you can see, right? Then as we learned from high school, momentum has to be conserved. Cannot just suddenly change. Momentum has to be conserved. So momentum is conserved at each vortex. Okay? And also, we have the integrate over this undetermined momentum. This is the so-called determined momentum or given momentum. Okay. But there are also undetermined momentum because you have internal lines. Okay. For all the undetermined momentum, you have the integrate over. In this case, it's just a k, right? See, there's a k. K. So we have the integrate over undetermined momentum. And we have to also deal with the symmetry factor. So we have to divide them by symmetry factor. Because symmetry factor is just a number. Again, associated with some topology. The related space case. Symmetry factor is the same. And last, the sum over all the possible diagrams. That's it. Okay. So almost the parallel to the position space Feynman rules, but the physical interpretation is quite different. You can see. Okay. As you can see now, in order to carry out this rule, let me repeat it for this particular graph. Let me repeat this process for this graph. We will see we can recover the result precisely. Okay, let's do it. So you tell me for each internal line you have to assign this one. Let me assign this as k. Okay, this internal. This means the internal lines. The external lines. Okay, for internal line I have a k here. Then I have two internal lines. Basically, I have two propagators. The point is, because I have a pi here, okay? These are the given data. Pf here. Actually, because of conservation, the pi equals to pf, okay? It's not independent. But anyway, for each vortex, the momentum is conserved. So if this is k, then this will be a pi minus k, okay? Okay? Only one k is independent momentum. All other can be determined by conservation, you see? Now there are two propagators for internal line, so you write down which kind of propagator each. Okay? Now for each vortex, you have I times coupling constant, like before, you will have Ig squared minus G squared. Okay? Okay? Now for internal line, no propagator, just given momentum. Yeah. Now momentum is conserved at each vertex. We already used it. Now integrate over undetermined momentum. We did it. Okay. Integrate over. Now divide by symmetry factor. Okay. The last step we haven't carried out yet because now we only for a particular graph. Okay. But in principle, you should counting all this to get a total amplitude, right? Because for given data, you have to think about all the possible processes. Now I only care the particular graph. So last time we haven't done yet. But all the others was done, right? So this is IM. Okay, so this is IM. Remember that also IM does not, right? IM, in order to resolve this constraint, you have to go to the S matrix. There is additional constraint. Okay. Additional constraint. This constraint tells you that EI has to be equal to EM, or the total incoming momentum has to be equal to the total output. Okay. Because momentum has to be conserved. Okay. So this is a cute exercise. From this exercise, we can extract this so-called momentum-based Feynman rules. Do you have any questions about these momentum-based Feynman rules?
老师，我想问一下，就是你那个就那个 LSD 公式，就上一节课你写的是那个就是那个算符嘛，正方形那个算法， 为什么你这个地方把它写成了 pi 的平方和 pf？是怎么去做了一下变化？
The same thing. Because box is it just box is the operator, right? You write box in momentum space is the p square. Or in another way to say it is from the formula with the box, you shift the box operator. Okay? Do this step. So before you do the p integral, then of course you get the p square. Okay? Yeah, you can check it. Any other questions?
就是刚才解释那个算符，它如果带上质量项的话是 box 加上
Yes, I always look about the answer. These two. Yeah.
它是在那个分母上的话，好像是减一方的。就是如果带上质量项的话，那个两个才能消掉。
打分它是 box 加
对 ，box 加 m 嘛。
一样能消掉。
Yes.
哦。
Yeah, just skip this square. Good question. Any other question? Yeah, the short answer is box is just a p square precisely. Okay.
你能够从
You go to momentum
推导这
space.
个东西，数学能推导这个，也是做了一个
Yeah, you can. Sure.
目积分嘛，作为一个我是
You transform the operator to momentum space is p square. Any other question about this momentum space Feynman rules? Okay, so let me give some remarks. This is the important chapter, so let's be more careful about remarks. So you might think about something like this, okay? You might imagine something like this. What happens if my graph is actually disconnected, okay? It's disconnected. For example, you might have some graph like this, okay? Okay, you might have some graph looks like this. And this is not only, but you have actually disconnected with another graph. Okay. One is this graph can represent something like 3 incoming and 3 outgoing. Okay. But as a whole graph, the pieces inside this whole graph is disconnected. Okay. Okay. You can check it. This is satisfy all these rules. It doesn't disobey all the rules. Becomes a bad graph. It's a good graph. Okay. This is a good graph. We already saw somewhere, right? In the position space, the graph can disconnect it. You see, remember that? The graph can, piece of the graph can be disconnected. Okay. Okay. I don't mean 2 graphs. Okay. This is a completely different concept. I really mean 1 graph, but it can be disconnected. Okay. You see? Of course, it's up to you. You might say, okay, I would like to understand this as 2 graphs. Well, if you understand this as 2 graphs, you have to go step by step. We can only talk about 2 to 2, okay? But now I want to talk about 3 to 3, okay? In the sense of 3 to 3, this is disconnected, okay? So in this case, so for disconnect, the amplitude factor Factorize means what? Factorize means that you can calculate the one and then multiply. Okay, multiply together. Okay, you see, for this graph, this kind of graph, you multiply. But for different graph, you have to sum. Okay, that's different different relation. You see, that's what I mean. This is not yeah. This is in the 3 to 3. This is it's connected. It's given by this multiply, which is so we learned how to read off the momentum space Feynman rules or amplitude result from the momentum space Feynman rules. Now let's look at another example. Let's focus on some 2 to 2 process of schedule. Okay. Let's focus on 2 to 2 because that's 1 to 1. You might complain that's a little trivial. Okay, that's a little trivial. Let's go to 2 to 2. Okay, but you know, following the rules is not a big deal. Just immediately you can write down the result. Let's carry another exercise. Carry it out. So for 2 to 2, again, let's think about the phi qubit theory. A qubit theory. Okay. So for 2 to 2, now I'm telling you. Now we think about the 2 to 2. So the correct way to count all the graphs looks like this. By 2 to 2, I really mean there's a 2 incoming, and there are 2 outgoing particles. Okay. So P1, P2, and P3, P4 are given data. Okay. Now fill in this graph. Fill in this graph. Okay. That's the thing you have to do. Okay. There's something here. There's empty here. You have to fill in this graph. Okay. Okay. In general, it's very complicated. You might see, you can think about it, right? Because there could be many loops, right? Many loops, you know, all the different orders. There are many. You have to use computer. But in the simplest case, let's focus on tree level, so-called tree level, without loop, okay? Without loop. If the graph has no loop, we call that the tree level diagram. Okay. So for tree level, this should be the easy exercise because theory I already tell you. Okay. For this particular theory, for the particular process 2 to 2 scattering, all this momentum I already gave you. Okay. Then you should be able to fill in this empty in this graph, right? In the tree level. Can you do that? Tree level means no loop. Okay. There's no some loop in the graph. Only the tree level. Now what is the possible graph? You can make it here. The first graph for sure is you can do it in this way, no? You do the phi qubit, right? The 3 vortex should appear, can appear. You see? This is the first graph. 2 to 2. What else? You can also consider some others, right? You can raise it into another. What's the other possibility? What is the other possibility? You can also go, you can leave the mother unit. You can also go in this way, no? Right? You also going this way, right? No, you see, I didn't change any given data. Okay, I just tried to use different building blocks to fill in this graph. Okay, this is another way. Actually, there's a third way. So these are called different channels. There's a third way. What's the third way? Third way is this is go here and exchange here. This way. Okay? This is also the way. Okay? You see? All these building blocks are satisfied. There's a 3 vertex completely fit with this given data. And there's no loop. Okay? So clearly you can see these 3 building blocks are different, right? But not the same one, you see? Because you represent a different process. So these are called different channels. So let me erase it. So this is the solution. So we call, in this case, there are 3 different channels. 3 different channels. Okay, 3 different channels. Let me write it more elegantly. First channel is E1, E2. E3, E4. Okay? I put an S, because this is usually called an S channel. And the second channel is the E1, E3, E2, E4. Look at the more this is called the T channel. Okay, with the T here. And last is the U channel. U. This is given by this way. Okay? For the U channel, you can check it. These are the only possible independent different channels, SDU channels. Okay, all belong to the tree level for this given to scheduling. Okay, these are all the only possible. Now, classification of the graph or all the possible graph was already found. Okay, what is the next step? Following 5 rules to write down the result. Right? Can you do that? Just following the rules I'm telling you. I was telling you a moment ago. Following these rules, write the result for these 3 graphs. It's easy, right? You do it. Okay, so let's do for the first graph. Now this is really easy because there's no loop, so there's no internal, there's no undetermined momentum, so there's no integral. Okay, no integral. So let's do just following the rules for this graph. For each vertex, I have to put a IG. Okay, so we have 2 IG. So there's only a single internal line, but momentum is completely determined. So let me write this momentum with P. For the momentum conservation, this is two incoming, P1 and P2. Then this momentum has to be P1 plus P2. Okay? And for this momentum, determine the momentum internal line, I have to assign a propagator with I epsilon here. There's only a single internal line, so there's a single propagator inserted here. That's it. Okay. I'm sorry. Let me first write it and then drop to the ball. Yeah. Okay. So this will be the result. So easy. See. So what happened for the second one? Also Ig, and for the propagator I, so this is P1 minus P3. And another Ig. Okay, that's it. For this one, Ig, I P1 minus P4. Ig. Okay, that's it. Yeah. These are the three results for this three diagrams. Very easy, right? Now, because these three channels are very typical scattering channels, so we give them the name STU. To be more precise, we actually define this as including this square. Okay, we define this as S, and this is a T, including this square, and this is U. Okay. As you can see, STU, because there's a square, STU are all Lorentz invariant. You see? Because you take a square, right? Square means Lorentz index is contract over. So STU are Lorentz invariant, and furthermore, you can check there is a beautiful relation. S plus T plus U equals to sum over all the mass squared. The sum means for the both incoming and outgoing particles. Like how many do you have? This sum, and you have to sum over how many. Okay. So since STU are Lorentz invariant, and in this case, you see, as you can see, I can express the amplitude completely in terms of S and T and U. Okay? Following the rules, for different graphs, you have to sum. You have to sum over the result, right? These are the different graphs. Okay? You have to sum. So the final result is a function of the final result is a function. Amplitude is a function of S and T and U. The point is all these variables, now the new variables, S and T and U are Lorentz invariant. You see? This is good because this result does not depend on the frame, okay? Because variable, fundamental variable is Lorentz invariant. You can choose whatever frame you like. Exactly. Okay, so this is the remarks number 2. Yes, do you have, okay, do you have any question for this 2-2 scattering tree level STU channel? So final remarks is third remark. Oops. So S matrix is not only defined perturbability, but can also be defined non-perturbability. Okay. You might say, okay, by now you're just telling me you do the perturbative calculations, right? Because you use graph. Graph is coming from you assume some small coupling constant to do order by order, right? Right? And but the point is, if you go back to the definition of S matrix, conceptually, S matrix, the concept of S matrix doesn't care you do the perturbative or non-perturbative. It's perfectly well defined, even non-perturbative. This is the final remark. In the practical calculation, we did it here, perturbative way, in a perturbative way. But this doesn't mean that S matrix can only be defined in perturbative. That's wrong. S matrix can be defined in a completely non-perturbative way. Okay. But the only challenging thing is that we don't know how to compute it. Okay? We don't know how to compute it in non-perturbative usually. But in recent years, there indeed some development really interesting that can tell us partially how to solve S matrix non-perturbative. Okay? For example, there's something called the S matrix bootstrap. There's something called the S matrix bootstrap. The idea is, let's forget about all this perturbative expansion. Okay, let's just try to look at the S matrix directly. Okay, and try to find all the constraints this S matrix has to satisfy. For example, unitarity, as we mentioned, the SS dagger has to be equal to 1, right? The unitarity tells us the S matrix has to satisfy this, and some other constraints tell the S matrix has to satisfy that. As we will see, maybe a few weeks later, there's something called the crossing relation. This S matrix also has to satisfy. Okay, then let's put all the constraints together and throw it to the computer. Okay, let the computer run. Maybe if you're lucky, you can solve it. Okay, in that way, we didn't use any Feynman rule or perturbative expansion, just non-perturbative. Okay, that's the final comment. Maybe we can have a break.
那可会正确放弃，那可会正确放弃，
当然有。那最简单的是，
所以这个就是对，给它写上去。
一个图里面给保质和成绩，那为什么没有相表？
不是，这是我感觉很多地方见到人。不是，那这其他那种太加这个把那个我连他的正回来。就是如果你想改第一篇可以改，第一篇我们就把这个我这是这样的，
让我们上一节让我们上这个推导，
他为什么外电
现在就是这条中间的，
我的话跟他这里地位有权，所以现在有没有？然后
上这个
这个的话就是就把这个叫这个这个区来要求，那为什么就确实
你看反过来，
他如果学的话，那不是可以
这个推导啊，对，
跟大家差不多，在这的阶段，就是把这手上
图是锁
对，那就是中间这条线说的，现在已经讲这儿，只要那个 space 接下来这张图相当于这种3个图形高阶，那为什么都是3？这两都是3，那这样连起来就是6。那不是啊？对，还是一个图的
它一个 order，然后当然强调 T square order，你当然可以画更多，
我作业其实就整了一些，
很容易画个明白。
我根本就忘记了他的地标什么时间。但是昨天一看发现是昨天晚上就了。那个功能是附加条告诉我，人工反馈有些给他工作，我给你做。我问他不是当年的中原创业，如果
那个也是应该大了，也就是每个景点都是 EX 的标，
哎，所以是圈越多，它就越多。
应该就够了。
这些都
其实是有
总结一下，那它应该
科学认同，但和这个连在一起。这个的上面就后面来说，就不用里面这个东西直翻这个，对吧？为什么为什么这个？哦，像那个。是吧？一零加一八，对，它就是这个是现在
哦，对，是要照完规定。
现在我找一找，
就是它的
这个区别是稍微有点的函数的。
对，没有系。
对，就这个地方。
这个它的这个这个
对，这里一，那里的一就是这里的 i。
它的对，就是说啊，
你看这个更清楚。没有，
都可以。
没有作业，
这东西，这个 RC 这个
有作业吗？怎么有作业？这个有这个，有那个，
你会发现你还可以让你反思清楚。我也那个我那个是，我在想是把那个Z 嘛，
所以这个就
自己的话，所有的我想这里这里。对，这里这里没有提到过，
它这个 M 是一样，
就是我们直接不考虑那个办法，
发现它可以，
也有打开麦斯，就看到后来谁把那个打起来，倒你知道我心我在想你。
按照某一些就两个好就行了，很简单。对，一个
其实你两个
写成这样子会有它这个是一个物理态，没用的物理，或者这里我觉得应该可以直接写成一个就是
对的，
那样一个式子的一个对，
那我觉得对，应该因为看那个他写成这样，然后我在想这个东西我们如何从这个式子图法去算的东西这么
高级，那就别的考试，
我的那个
飞我大好看，说今天大飞也会被人更神奇，把成一个乐器，就在那些味道还算会有
这个面这个工作地方哪里还有？我就 FZ
很多队友。
12的地方，
你们现在最上面的地方，
还有一个这个结果，一两个小时就交床，还有这个小时不要改，有没有武器啊？这个小题你说嘛，别这个小题，一个你觉得大有几个大题？你可以还是这样？你说大题，
要不一下子，
别的，下次下。
电脑我们的这个视频，才绕一圈就几点？不对，是我在说，好，我这边是凯特的，给我们小
Excel 出题，回去开电台，
这个
就是是不是讲那个历史之类的东西？
一两个就要讲，
一个不行。
这个
怎么说？
想问的是，就是他们之间的关系，就是
他们叫拜特
这个
但是就改成拜四了，
我知道。
它那个如果就不一样，给这个4-0，
是只能有4个零，谁的图？
它这个展不一样，它
这是因为发现嘛，这样
就是你克它这个最多只有5-4和5-5的，为什么？因为5-5、5-6在写上而且他认为要非常高的能量
啊，因
5-5
为那个量体很少。
最多是5-4，
我觉得好像不是，就是因为这个等于怎么说？因为它是那个就是那个
它这个对应的
没有坏太阳。背开
然后
偏优败的，
然后在那个它确实是可以，对，
我的意思是，
嗯，
如果不改变这个的话，
会记它我不太确定，就是可能这个，但这它证明了它也是因为是那个，它是只是差一个出现了，所以它就是，但是我觉得
拜三，
它是以今天有定义对吧？VP，如果 AP 定义成或者那种汉语，完整汉字要这个限定的时候，VP 已经超过一般的话，
然后写出高分，
哪套好像
不跟最大的
对，
如果它只有一个，如果它就写这些，只有一个这个拜，然后对不？
后面知道动量空间上，
正面那个
对，后面它的那个动量空间在它用在后面的话，
就是在那个对不起
中途出几个问题，几个问题。
就是这种，就最开始的。
那你们在说白
啊，发现我后来发生这样的事情，
下面这个设计也是指在
哦，这个就是
只在 free 上。
嗯，
那 anyway simple word 说两次。对，我们现在问的就是说最基本的定义的这个 market theory，
因为它是。
它简单就只是说最低。然后你根据某一个 energy 对比，的话呢，
就是没有这个
That's right. That's right. You didn't mention it. Five times the biggest. That's all you have. 因为我们快餐简单一点，我们用快餐的这个这个的话，可能这个人可能没有你先 follow 的这个。
对，你得用我
最近它太有想法，所有的它上
这个技术，它基本上是一个。
这个是什么关系？
啊，应该可以证明可以先教你。
还有是那个，然后我是这个跟
可以证明
它真
这个对吧？就是这个它的题目最开始。 学长，
啊，也
只有一等于是两个，但这里我只有一个。
只有
就是一当时量体。考虑分法，快3个。
那个以前好多。
考虑这些，
我觉得那个人都想把讲一起来。
个人忘了。
但是 in general 你可以考错。你可以考虑分子，就是没有人，他们也有这样的30。in general 可以。那如果你的 series 足够复杂。这样微啊，对，因为有好多个意图，这里一个讲就有，所以是分个品。
有很多点，
这个他定在一种，
没有啊，这是把它求去往那考。
就类似
你说多个数据的混合动量。
这个概念做一个比这个，这个系统没有和之前都有他们。还拍着我看到，所以说确实就是不是你在验视的，我在忘了，他们跟我是拿的真正的实际情况，也是能个人这个他们就是会但是还是真语气上有的中就在是把这个地方很多人这个地方他们也把这个然后但是你记得当时有个中国人当时我们有在你的10分还行，他都没听哇很多我就是
已经处于一个非常基础的这个还是基础就是它是表面的，这个人面对的，所以这个动物是很明显的，这个质量开始就或者表面规模一些原件这种大概的话，就是一种交替的交合台压房子这样的产品。哎，你条件那个审问上是常有这不叫对算的发现，这种比较好的，按照原则来办一个房子，你我其实你见到就是表那个职业为有，写出也你的那个是中文表象可以写出来，这我们。有一个主播一方面，有提取这些，它现在就相当于可以做什么的那种。
Okay. Let's continue. So after now, we basically finished the discussion about spin zero particle, which is scalar. Okay. Did you hear about the spin of the scalar particle in zero? Do you know what is spin? Does anybody? Is there anyone who doesn't know what is spin? What is spin? Now we discuss. We did all the discussions. We discussed all about the scalars. Okay. We didn't touch any other more complicated field, but we introduced some concept like vector field, tensor field. When we try to when we introduced the Lorentz group or Minkowski space in the very beginning, right? Then naturally you might imagine there could be more complicated field, vector fields and tensor fields, spinor fields, right? There are such kind of fields. That's our real world. In our real world, there are also such kind of particles. So this is the next step. Next step, we're going to move to the discussion for more complicated, or for the particles have a more complicated structure. And of course, this course is to using this field theory language to describe particles. So it involves more complicated structure fields. Then we also learned, even for the scalar case, we also learned how to describe the single particle state, right? So you still remember that? What is the single particle state? We use the AP dagger, act on the vacuum, right? In the free theory to describe a single particle state, okay? Then the natural way to classify different particles is to fall in this way, okay? Fall in this way. What do I mean by that? Fall in this way. So we have to think about it carefully, how to understand the state, okay? Particle state. particle state. That's a good language, natural language to discuss. So previously, only in one case we make this very clear. Okay. We make this very clear. We basically just use the we use this AP diagram back on the vector. Remember that? Okay. Or in other words, we use the like P state represent a single particle state. Now, since we want to discuss more complicated particles, okay, you have to specify which particle state you can write down. Which, or in other words, which state can represent your particle, okay? So that's the question you can ask. But this is a little bit complicated question, right? It's not a very easy question. So where should we start? What about the question is what about the other particles? This is the single particle state for scalar, okay? For scalar. Then you ask what about the other types of particles? We know in our real world there are also photons, electrons, muons, okay? There's Wigners, there are spin 1 particle, there are even in other nuclear physics, there are even higher spin particles, okay? So what do we do about that, okay? Okay, you have to understand how to use state to represent the other particles. But if you just ask one by one, say for an experiment from HC, I found a new particle, then I ask myself how to using the mathematical or physical language to describe this particle. This is a little weird because you just ask case by case, right? It's better to develop where if you are serious, we want to just develop a very systematic way, okay? You just classify all the possible particle states. Then it will be very good, right? Indeed, this can be achieved, right? This can be achieved, and this is so-called. You might hear about this. So-called Wigner classification. This famously was already classified by Wigner in 1939. So we're not going to prove it. It takes time. We just compare the Wigner's result. It's a widely accepted, rigorous result. Okay, to classify different particle states. But before that, before I tell you the result of Wigner's result, we need to do some preparation to prepare some knowledge to understand what Wigner says. Okay, Wigner says. So what is that preparation? Preparation is the first step. We have to make it clear the entire symmetry of our space-time is the so-called Poincare group. What is the Poincare group? It's simple. So we already understood what is the Lorentz group, right? Okay. We already understand what is the Lorentz group. So what is the Poincare group? Poincare group is nothing but the Lorentz group plus what? Anybody knows? Right. Translations. Because in Lorentz group we didn't include this translation. Of course, we know translation is a good symmetry, right? Right? You translate from this place to that place. The experiment is going to be the same. Okay. So the translation symmetry plus Lorentz group form this so-called Poincare group. So this is really a God-given symmetry for our space-time. Okay. Then we're going to describe our real world. So of course, all the particles surviving our real world should fit into this symmetry, because this is the God-given symmetry. What do I mean by that? We also discussed previously about how to transform a state. Remember that? If you have a symmetry, you can talk about do the symmetry transformation, right? For example, you can translate this to there, okay? You can rotate from one state to another, okay? Okay? So particle state has to fit with the space-time symmetry or the Poincare group, okay? Meaning that you can always, in an elegant way, you can transform this state under Poincare group, okay? You can do Lorentz transformation, you can work with translation for these particle states. Then you can go from one state to another state. So what I mean by that is, okay, let me first write the word. Okay, suppose, okay, what I mean by that, suppose the particle state is described by some aside state. Okay, suppose this is my state. Okay, suppose this is my state. My point is, under the Poincare transformation, this state has to be P to distinguish with momentum. And P like this. Okay. It has to be transformed to another state, right? This P can be translation, can be rotation, can be Lorentz boost. Okay. Can be Lorentz transformation. In any way, you just send it from one state to another state, good particle state. Then in this case, we call state or a set of state. A set of state aside is a representation. It's a representation of the Poincare group. This is very natural, right? This is very natural, right? Because this state essentially there's a settled state, okay? There's a space, or maybe hyperspace, for this state. Now, when you do symmetry transformation, you go from this state to that state. So basically, the state represents how the symmetry transform, right? Is that clear? So we call this is a representation. Now, when you talk about representation, you can also talk about something called the irreducible. Can anybody say what is the definition of irreducible? Okay, what is irreducible? Irreducible essentially means that there is no subset of the state. They transform only among themselves. Okay, is that clear? So you have a set of state, you have a space of the state. Then when you do symmetry transformation, you jump from this to that to that to that. Okay, then there's a good representation. But the point is, sometimes there is a small subset of the entire big set. Okay, symmetry transformation is only happens among themselves. Okay, they don't mix with the remaining part. So in that case, we call it reducible. irreducible means there's no such kind of subset. This is just a group theory concept. Okay, if you are not familiar, it's fine. I'm just telling you, explaining to you what it means. So irreducible means there's no subset. Transform. Only among themselves. So now we understand what is irreducible. So next thing we have to understand is something called unitarity. We emphasize a lot, okay? Unitarity. So symmetry transformation has to be unitary, right? If it's a physical symmetry transformation, it has to be unitary. Why? Because the observable is quite often involved the inner product of two states. Okay. Then if you transform both, the physical observable is often related to the inner product. Something like psi 1 inner with psi 2. Okay. Okay. This means under the transformation, this becomes what? This becomes psi 1 p. We use p to represent to denote this transformation. Where is my p? Here, that's p. It means that under the transformation, this will represent to p dagger p psi 2. Okay. You see? So this p dagger p better to be identity, okay, in order to preserve this observer or inner product. Okay. Because this inner product is not sensitive to under the symmetry transformation. So this is the definition of the unitarity. Okay. We also saw this before, right? Previously, right? When you do the time evolution, you use Hamiltonian. Okay. When you do the space translation, you use momentum. All those operators, if you write this, previously we call it as U operator, right? U is essentially named for this unitarity reason. Okay. To emphasize the symmetry transformation has to be unitary, right? Okay. Because you don't want to change your amplitude under symmetry transformation. Okay. So this p dagger p has to be 1. This is the definition of unitarity of p. Now, so we understood what is irreducible and what is unitarity, plus all the particle state has to represent to the God-given Poincare symmetry. Okay, see, because the particle is living in this real world. Okay, and the real world is the God-given Poincare symmetry for the space-time. So particle state has to represent this Poincare symmetry. And now, after we understand this irreducible and unitarity, then we are ready to understand this Wigner's theorem, Wigner's classification. So let me write Wigner's. So what Wigner found is first, irreducible unitary representation uniquely classified by M and J. What does this mean? M is just the mass of the particle. J is the spin of the particle. Okay? Why? It's very natural. We understood the mass very well, right? Because this mass is rest mass. Rest mass is Lorentz invariant, or it's Poincare invariant, right? Right? You'd better to use the invariant object to classify your representation. Is that right? Right? It cannot be invariant, right? It has to be invariant. If this quantity is always changed after your Poincare symmetry, then how to classify it? You know, it's weird, right? It has to be. It's better to use this invariant object to classify the representations. Okay. So a typical choice is the mass of the particle. Another good choice is the spin of the particle. Spin of the particle is also invariant. Here, the spin, I really mean this. This total spin is not some projected. It's not some projected spin. Okay. So we will see. So, but as a mathematical result, if you accept Wigner's proof, to understand this final result, it will be very easy, right? It just says that if you tell me, the mass and the spin of the particle, I can basically fix the representations. Okay. So, but in detail, here M is a non-negative real number. Okay, as we also understand, because mass can continuously change, right? 1 kilogram. It's a real number, but it's non-negative. It can be zero, right? Zero means the particle is massless, like a photon. Okay, like a graviton. Okay, these are the massless particles. Okay, so it's non-negative real number, and J is non-negative. However, it's signed differently. For J is also non-negative, but it has to be half integer. Half integer means like 0, half, 1, 3, half, blah 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 blah. Okay, can only take value in this group. Okay, this is J. This is for J. And this is just two numbers. Now, furthermore, this is the claim number 1. Claim number 1. All the irreducible unitary representations can be classified by M and J. By M and J. Okay. So in detail, claim number 2. So if J is positive, then for each value of momentum which E square equals to M square means on shell condition. Okay, under on shell condition, for each value of momentum for positive spin particle, there could be 2J plus 1 independent states. If M is positive. And there can be only 2 independent states. If M equals 0. Now, this leads to further understanding. So let's try to understand what does this mean. This says what? This says, let's use one example. Let's say, for example, electron. Okay. Does anybody know what is the spin of electron? What is J for electron? 1/2. Very good. For electron, it's 1/2. What is the mass for electron? Just tell me 0 or not. is non-zero, right? The mass of electron is non-zero. So let's try to fit into this category. So certainly electron J is greater than 0, right? It's half. Okay. Also, electron has a positive mass. You see? So its category belongs to here. You see? Is this line. You see? Now J equals to half. 2J plus 1 is equals to 2. Okay? 2, right? So this independent state essentially means this the spin of the electron can be up or down. Okay? That's what we mean. It's kind of internal degrees of freedom for electron. Okay? Because there's a spin, intrinsic spin there. That spin can be up and down. Even you fix all other quantum numbers, okay, of the electron, still there are 2 degrees of freedom. There are 2 choices. There are 2 choices of the spin. Can be up and down. This is what I mean by independent state. Okay. Now, why we specify here for each value of momentum? Because in order to talk about the remaining independent state, you have to specify all other quantum numbers. Momentum is a typical quantum number. Of course, you can change your electron from momentum P1 to P2, right? These are 2 different electrons because they carry different momentum. But even though the momentum is fixed, okay, there's still 2 independent spin state, okay? Because the electron spin can up and down. From here. Now let's examine something here. Let's try to find some other massless particle, for example. What is the best choice? Photon. Okay. So for photon, m equals to 0. What is J for photon?
1.
Yeah, J equals to 1. But this says that it doesn't matter what is J, right? If m equals to 0, there can only be 2 independent spin states. Indeed, this perfectly consistent with there are only 2 polarizations for photon. Okay. For photon, there are only 2 polarizations. This polarization is essentially coming from the spin. Because spin equals to 1. And photon carry massless, so there are only 2. Another example is what? Graviton. Okay? Graviton is another example. Graviton also belongs to m equals to 0. Even though graviton has spin, what is spin on graviton? 2. You have 2, but in any sense, you can only carry 2 independent polarizations. Okay? That's indeed fit with this gravitational wave. Okay? If you solve a gravitational wave, indeed you can only find 2 independent polarization. So now you can realize the Wigner's theorem is so powerful, right? It's just mathematically proved all possible existing particles. Okay, they only happen in this way. Okay, they only happen in this way. Okay. Now, for sure, this is a condition is only for positive J. You can further ask what happens for J equals 0. What happens for J equals 0? J equals 0 is the case we are very familiar. What is that? Huh? J equals 0 is what? Is a scalar, okay? Right? J equals 0 is scalar. J equals 0, only one state. For each E. Both, this is true in both m is positive or m equals 0. Doesn't matter. Okay. So as said, I will skip the proof of this one. If you like, you can find from Weinberger, for example, volume 1, find the proof. So we understand basically now the classification of the particles. Classification of the particles. Let me give you one remark, which is important. I want to emphasize that we classify here, Wigner classify here from the group theory. Okay, we emphasize that this is irreducible and unitary, and it's a representation of Poincare symmetry, right? But let me emphasize, these representations are all infinite dimensional. Can you see where the infinite dimension come from? It's not a finite dimensional representation. Can you see that? Can you see that? This is a remark. These are the infinite dimensional representations, right? Because at least from one place you can see it, because P is a continuous variable. Okay? P is a continuous variable. It can take infinite different values. Okay? Each P represents a different state. So you can see this representation is actually infinite dimensional. It's not some finite dimension. Actually, there's a mathematical result. There's no finite dimensional unitary representation of Poincare group. Okay? It does not exist. No way. But we do know there are good physical particle states. So the particle states all belong to infinite dimensional representation. Okay. This solves sometimes the confusion. Somebody may just raise their hand and say, okay, why this is so complicated? I can easily find some, for example, some easy, very simple vector. This vector may transform nicely under the Poincare group, at least Lorentz group, right? You see, if I have a Lorentz vector should transform nicely under Lorentz group. No, it should, right? It is. But the point is, those simple choice, the representation is not unitary. Okay, it's not a unitary. So unitarity is very, very important here. In order to get a unitary representation of Poincare group, the representation cannot be finite dimensional. You can check yourself. If you don't believe me, just check yourself. Okay, check yourself. Just play with a Lorentz vector. Lorentz vector may transform in a nice way. But the point is, this representation is not unitary. And as we discussed, for particle state, we really need a unitarity. Otherwise, the violate physical law. Okay, the violate physical law. You see, for example, the norm of the state. We know this is something probability. Okay, related to probability. This cannot be changed under simple transformation. Okay. If it's not a unitary, then it's gone. Yeah. So we don't want to violate. So we need a unitarity. And in order to find the unitary representation of a Poincare group, you have to really work hard. Then eventually you find the finite dimension choice does not exist. The only way is to go to infinite dimension. Indeed, now we justify ourselves. This particle state we found from quantum field theory to quantize a field. Okay. At some point we already mentioned it because quantum fields including infinite degrees of freedom. Okay. So only from this quantize a field and then get a particle state, you find, oh, this is a good choice. We really found this good particle state as a choice to unitary irreducible representation of the Poincare group. That would happen. So this is a remark. Then the next thing we want to discuss is how to combine with the field. We already mentioned the field. Field is a choice. Field theory is a choice. After you quantize, you can get a nice particle state to fit with everything. Okay. Now there's a gap. It's a small gap between particles and the quantum fields, as you can see. Wigner only tells from purely group theory, mathematically, to classify them for all the particle states. But Wigner doesn't tell you which quantum field theory can incorporate this particle. You see, right? There's no Lagrange or action message from Wigner's theorem. You see, but we really want to find which quantum field theory to describe these particles, right? So this is the next question: how to marry this particle to the fields? Okay, which kind of action of the fields or which type of fields can incorporate this particle? This is the next question. But this question should be very straightforward, based on the counting degrees of freedom. For example, in this case, J equals 0. I already mentioned, okay? You don't need much, you see. For J equals 0, you only need one state, you see. This theta means what? This theta really means the intrinsic or internal degrees of freedom for the object. So in this case, you can easily guess the scalar will be a good choice. Scalar field is enough because scalar field at every space-time point it represents 1 degree of freedom, right? Because you can change the value of the scalar. Okay, you can change the value of the function. Then it means there is 1 degree of freedom. Indeed, it fits with this one. Wigner is this one. Then the natural guess will be scalar field can incorporate a J equals 0 particle. Indeed, it's true. So we call it, in this case, a scalar particle. Okay. We also mentioned a few weeks ago, in order to build up a good field theory, you have to vary several issues, right? Remember that? For example, locality, Lorentz invariant. Remember that? Or now in this case, maybe Poincare invariant. Poincare invariant, locality. Okay, what else? Yeah, there are a few constraints. Now, since we emphasize the unitarity a lot from Wigner's classification, you might also ask, can we put unitarity as a constraint for this field theory? Okay, of course you can, because once you quantize it, you can impose unitarity very easily. But before quantization, it's very difficult to talk about unitarity. You see, because unitarity is about quantum state. If you don't have quantum state, what do you do for unitarity? Okay, so at classical level, it's hard to talk about unitarity, but we can talk about something else. It's like energy bounded from below, or energy has to be positive. So we construct the field theory and impose these constraints. So energy bounded from below means what? Energy bounded from in flow means there is a noise energy, definite noise energy somewhere. Okay. It cannot be minus infinity, you see? Because if it's minus infinity after you quantize the theory, we know there is something called tunneling, okay? You can, in quantum world, it can always happen, okay? You can jump from one state to another state. If your energy is not bounded from below, it means the state is always allowed to jump into the lower energy state, okay? Then the bad thing, the worst thing is that there's no stable ground state. Because you can always decay to the lower energy state. Then the system is bad. Okay? Because you don't have stable ground state. How do you excite based on this ground state? How can you talk about, observe physics, all the state about on this ground state? Okay? So energy bounded from below is a very, very important criteria or constraint. Even in the classical level, you can you can easily find. Somebody just asked, we just talk about the lambda phi cubic theory, but if you check the energy, whether the energy is bounded from below, you realize the lambda phi 4 is better than phi cubic. Because lambda phi 4 is bounded from below. Lambda phi cubic is not. Okay, you see, phi cubic is cubic function, right? The cubic function. It's not bounded from below. Okay. Okay. This is just remarks. So let's quickly justify a little bit what I just said. So how to embed these particles into a field? How do we know which kind of field theory can incorporate Wigner's classification? This is the next question. Because we generally talk about the different particle with different mass and speed. Now, next step is how do we go from particles to fields. Then for the easiest spin zero case, we know we can use the scalar field. Okay? Because you only need 1 degree of freedom. Okay? And indeed, we already know the easiest, simplest theory for the scalar. Example, free fields. The random is this way. It's written this way. And there's also equation of motion. But the most important thing is we want to check is energy. Energy density is this zero component of the energy momentum tensor we defined from another theorem before. Okay, the T not null. You can work it out. The T not null in this case is not null. Partial L, partial phi dot minus L. Okay. Now this is a half partial T phi squared plus this phi squared plus m squared phi squared. Okay, you work it out. You see, this is positive. You see, this is indeed positive. This is indeed positive. Because all that square. Okay, square with plus sign. So this is indeed bound from below. Positive. It satisfies the energy, positive energy condition. So it's a good theory. Okay, it means this is a good theory. Okay. Now what else? What happened for spin -1? We want to move to spin 1. In spin 1, if M is positive, how many independent states? How many spin states? 3, right? J equals to 1. M is positive. There's a 3 indeed. So there are 3 degrees of freedom. The number of degrees of freedom equals to 3 if M is positive. Okay? I don't have time to go through how to cook up a field theory to incorporate this case. So there is a nice answer. If you like, you can find it yourself. Indeed, in this case, there is a very nice choice. Lagrangian goes in this way. Okay, you can incorporate this case. Spin 1 massive case. And you can count the degrees of freedom. Indeed, there are 3 for this field theory. Now this is such kind of field theory. This field theory is sometimes called the Broca Lagrange. It's not Maxwell. You might say, okay, this is part of the Maxwell, but there's a mass term. Okay, this is the Maxwell theory deformed by a mass term. Okay, this is called a Broca Lagrange. Broca Lagrange. Or sometimes people call this a massive vector boson. Okay, massive vector boson. Yes, as you can see, this is a massive. It's not massive. Now, of course, the massless case, the number of degrees term equals to what? Of course, 2. Okay. Now, this is our most interesting particle, right? So this particle is photon. And of course, we know the theory already. Photon is described by which theory? What is the theory prepared for photon? Maxwell's theory, right? Maxwell's theory. Now the point is, I think apart from the details, the point is more important. The point that I'm trying to discuss here is, suppose you live in the age before Maxwell. Okay, you don't know Maxwell's theory, but instead you know Wigner's result. Okay, of course this is not possible, right? Because Wigner is much later. But suppose Suppose you know Wigner's result, but you don't know Maxwell's theory. What do? You should try very hard to find some candidate, okay? Some theory can incorporate this degrees of freedom. Now, in this m equals 0 case, you have 2. Then ask yourself, which field can incorporate 2 degrees of freedom? Scalar, of course not, okay? Maybe a pair of scalar, it looks like, but you can try, then finally you have some trouble. Then you throw it away, something like this. Now, you jump into, what about the vector field? Vector field, naively, you have 4 components, right? At each point, right, you have 4 components. They may say, okay, I have 4 degrees of freedom. 4 is greater than 2, right? 4 is bigger than 2, right? Is that right? Now you have 2 redundant degrees of freedom, right? So you have to somehow cook up your theory to really make there are 2 redundant degrees of freedom. Then you succeed. Okay? This is what Maxwell did. Okay? This is not what Maxwell did. This is Maxwell's theory. Okay? Okay? So in this case, of course, eventually, but let's jump over this process, okay? Because we already know that Maxwell's theory is the correct candidate to describe photon. So let's do analysis to try to see why Maxwell's theory carries only 2 degrees of freedom. Why Maxwell's theory carries only 2 degrees of freedom? Okay. Is there anyone who does not see this before or does not know this language? Raise your hand. So everybody knows. Okay, so I can escape how to get this one, and how this is connected to the Maxwell's equation. Yeah, maybe a brief discussion. So this is Maxwell's theory. More precisely, this one, okay? And what is the F mu nu? F mu nu is the function mu. Mu. Okay? So F called the field strength. A is called the gauge connection, okay? Or the vector field, if you like. And from here, you can derive the Maxwell's equation. Equation of motion is essentially this one. Okay, this is Maxwell's equation or equation of motion. This is the equation of motion from this Lagrange more precisely. But there is also a Bianchi identity. There is a Bianchi identity. So combined with these 2, combined with this 1 and 2, you can recover the usual Maxwell's equation. Okay, there are 4 equations, right? Maxwell's equation. From 1 and 2, you can recover that one. You can recover the famous Maxwell's equation. Okay. So let me escape this one and give you as an exercise to check yourself. Because we only have several minutes. Yeah. I don't think I can finish. Yeah, let me mention, maybe you can go into details next time. So for this theory, there is a gauge redundancy. For this theory, there is a gauge redundancy. For example, you can transform your A mu fields go to A mu x plus partial mu for an arbitrary function lambda x, then this does not change. Okay. You can check easily, very easy. Okay. When you change a in this way, this Lagrangian does not change. Okay. But this is a little bit different from the symmetry transformation we mentioned before. Remember that? Previously, when we introduced the symmetry transformation to prove Little's theorem, we always say, so let's try to translate the fields, right? Remember that? That translation can represent it as some phi plus some alpha delta phi. Remember that? There's some operators, right? But the point is that transformation, everything always act on the field. Okay, but this is slightly different. You see, for example, this is nothing to do with this. No, this cannot. Don't need to write this piece as some operator act on the fields. Okay. This lambda is just some arbitrary function. That's some arbitrary function. So indeed, physically, we call this is a gauge redundancy. It's not a symmetry. It's not a symmetry. A gauge redundancy. Okay, a gauge redundancy. The point is, from experimental, no experiment or no physical observer can detect this lambda x. Okay. Okay. You know, theory is always justified using experiments. Okay. Okay. We're not the God. You cannot just say from the beginning, you know, which is the physical, which is the unphysical. It's not true. You always justify your hypothesis using experiments. After the justification, then you leave it. Okay? Then you make it as a rule. In this case, it's also true. There's no physical experiment that can detect this lambda x. So we don't think lambda x is physical. Okay? So we think this, even though this is nicely invariant under this change, but we think this is a gauge redundancy. Okay? It's a gauge redundancy. What do I mean by gauge redundancy? Gauge redundancy essentially means that this is not a physical transformation, but rather this is an equivalence. Okay? You see? This means that if you shift the a mu x by this amount, it's not distinguished from a mu itself. It's just equivalent. Okay? It's just equivalent. Then you may ask me, okay, you just tell me lambda x is an arbitrary function. Then this equivalence relation really means there's an orbit. Okay? It's not just 2 points are equivalent. There's a line. Okay? There's a line. There's a line. Means what? Means that once you have a gauge field configuration somewhere here, then there's a line. All these points on the line are equivalent. Okay? This is called a gauge orbit. Okay? Now, if you have different gauge field configurations, then you have many orbits. You see? As said, right? Very natural. Because all these 2 objects are equivalent. Then you can change your lambda. Change your lambda means you run over this line. Okay? Then picture-wise, you can draw a lot of gauge orbits. Okay? The point is, once again, the line only represents one physical configuration. Okay? All the points are equivalent. Now, sometimes we also do something called a gauge fixing. Gauge fixing in this case essentially means you choose a section. You know, you choose a section across all the gauge orbits. Since you tell me that it doesn't matter, this is all just equivalent, then I can choose whatever I like. Okay, do the calculation. Finally, the physical result is not dependent on this choice. That's what happened. And and you can also check for sure. It's not only this L is the environment, F itself is the environment. Okay. We also understand that F itself is related to the magnetic field and the electric field we observe. Okay, from the lab. These are very physical objects, right? Quantities. Because these are electric fields and the magnetic fields. Okay, we already detect that from the experiment. So F is more physical than A in some sense. So this kind of change does not change in F. Okay. So it's not surprising. These are just the gauge redundancy. It's not a symmetry. Okay. So, okay. So remember, one word, gauge symmetry is not a symmetry. This looks a funny statement, but it's true. Okay. So I think gauge symmetry is not a good name. Okay. We should call it gauge redundancy. Okay. The gauge redundancy is not a symmetry. Should remember. Okay. Yeah, I used up this time. Next time, maybe we will continue to discuss why photons has only 2 degrees of freedom and how to quantize photon. So the following quantize better field. Okay? Let's stop.
就是说你因为这个没有，他是
指标样
因为他的这个讲座讲就是他主要讲，所以说大家是这边听我就当做经典讲。有的，应该会
哪个地方选一个？
我在上课也说了，不知道在哪用。
这个厂也有，
那我这个是这个黄段的，但我第二个
张亮上
好的好的，
我不确定是啊，
这条线是他们APU 都是。
就是每一个点是 very semantic， 每一个点对一个 field conclusion， 它构型会分公司的用处，对每一个东西的 conclusion， 但你比如说这样一个 conclusion， 但是因为它一直是 many choice， 所以你把一个
所以每一条线是不同的这个，
这两个点，
这两个点的不同在他们的 A B 中。
对。
不是一个 A B。
我也没看到这个图。谢老师问说，这个用大力银河，它可以有
应该是
那用你讲的，
还有
这个是算什么？
当然可以有。
还有实际上它主要是
哦，你是哪个？
不建议。
对，
Let me say， 这里面没，这里面没有呀。
如它加一个欧洲的想法，
它就不叫。
就是
这个它例如这个还有一个那个
画一下。
这两个起源。
所以原来是法嘛，
日子开的
偏牛那种
它的长或者几句
那个，但是它好像加强
它的这种，
然后每个线是这个线是快点
它的起源到
这个就是它的给指导线，
所以说它多了一个
到这儿，这个0.2就反 A 米，
因为
对，
对有质量是有都在，
所以它就是一个给指
加强
物理 object 上的所有场都是由一个给指关系联系起来的。对，那问题是那个量化的时候就选择一个，
它是4嘛，要加个归数，
所以不等价的那些场的那些
随便画一条线，
就是每一个轨道上，就是每个轨道上取一个点，每个轨道上取一个点，从每个轨道上取一个点，
再一个，
物加相数是
一个槽体
OK， 所以
然后每个槽看
OK， 所以就是就跟垂直的那个就是这个从切面
有一个元素
肯定要 check
原理它检讨了答案，它不一定要简直看这个槽，它可以这样看。
只要搞定。
所以你画的时候其实
像随便这样
这就是场景，
你也可以这样，就这样 check case，
那它一定自由度
比如说你加的是什么？
然后它的那个分析它
facial motion，
或者这个 OK，这个副卡应该用下来。
为什么做一样不进
对，
肯定够，所以
是叫够到现在知道把那个
这个相对来说，对，相对来说，这个非常来准，因为
交给你了，
非常长，有的是一个，5、3也是，5、4也是，对吧？应该没有，但是应该没有。
没有学过电脑力学，
这个像在H 维根是真的。比如说，你可以 very naively， 你可以认为这个是某种像是自然规律，因为这是 dynamic term， 这毕竟是对吧？这有认为数字啊，然后你这个相改，这个从
对呀，
你这里可以就是它的 formation 可能 tier 这样，你可以就是问。
我主要是我想的是，
对，就是要想。
啊，我那时候在做另一个东西的作业，写我程序，然后写完之后才发现，诶，怎么还有个滴滴？一天晚上，没事。
1.8才会行，3.8才会讲完。
那是做的那个
练啊，讲没有？
你也是，对呀。
对，我们就是他不是会去讲嘛，因为像我为什么说，你那里有位置假设，我们也不没办法，都有自己的。